Wonderful. Okay, I don't see you, Gary, but maybe I don't have the right picture here. I'm not sure, but I see your slides in any case. I don't hear you either, though.
Okay, so
oh yeah,
can you see my slides and my pointer?
Now I see your slide, I see you, and I hear you. Very, very good.
Okay, hang on a second. Let me show. All right.
Okay, so the next speaker is Gary Shiu from University of Wisconsin-Madison, and he's going to talk about microscopic description of brane gauginos. Thank you.
Okay, so thank you for having me here. I will be talking about joint work with Yuta Hamada, Arthur Hebecker, and Pablo Soler on the microscopic description of brane gauginos. Now, I don't have to emphasize to this audience that non-perturbative effects play a decisive role in string phenomenology. Since the 80s, they have been used in moduli stabilization. By now, we know of other and perturbative ways to stabilize moduli. Nonetheless, gauginal condensation of branes or rare Euclidean D-branes are still key elements in many proposed de Sitter constructions in string theory. Now, in the presence of branes, these non-perturbative effects can be localized in the lower dimensional subspace. This introduced subtleties, as first noted in the Hojover-Witten construction. So a gaugino bilinear, denoted by J here, sources a bulk four-form flux. As a result, the four-form flux diverges when approaching the brane locus. And the 11-dimensional supergravity action is UV divergent on shell. Now, the fate of this divergence was eventually understood. The underlying 11-dimensional supersymmetry suggests the presence of a quartic gauginal term. This completes the action to a perfect square and ensure that the divergence is cancelled. So only if this UV divergence is properly regularized can we extract physically meaningful results. So our work is a continuation of this quest. And as you will see, branes with codimension 2 and above introduce new subtleties. And the problem is a lot more challenging. But the good news is a properly regularized local actions for brane gauginos up to quartic order is finally available. Now, a frequently asked question is, what is the point of this microscopic treatment? Gauginal condensation is an infrared phenomenon. Can we just be content with a four-dimensional effective field theory description? Now, just to be clear, what we are after is not the gauginal condensate, but the proper 10-dimensional origin of the gauginal couplings. So given a UV model, it is important to understand how various microscopic components, such as the fluxes, various supersymmetry breaking sources, the gauginos, as well as other non-perturbative effects, how they interact with each other and with the background geometry. So four-dimensional effective field theory arguments alone do not tell us why certain couplings are small. And we can already illustrate that with codimension 1 branes. The Hojover-Witten construction has triggered an industry of brane world phenomenology. And a lesson from this trade is that various low energy degrees of freedom can have different profiles transversed to the branes. So understanding the four-dimensional effective field theory describing this low energy degrees of freedom required knowledge of these local couplings in the higher dimensional origin. Now, an accurate description of these bulk brane interactions is even more crucial in string theory because of the Dine-Seiberg problem. So as you know, the Dine-Seiberg problem states that a stabilized vacuum can only arise by balancing terms of different orders. So weak coupling vacua would therefore necessitate small numbers in the EFT. For example, in KKLT, stabilizing the Kähler moduli at large volumes require W naught to be exponentially small. And to ensure that the anti-brane uplift does not destroy the minimum, the warp factor has to be of the same order. It's necessarily small as well. So the effective field theory descriptions of weak coupling vacuum is nothing but generic. So a microscopic treatment is necessary for substantiating these constructions, for example, explaining why these numbers are small, as well as quantifying corrections to ensure that the higher order terms that we neglect are indeed negligible. We need to have complete theoretical control on these couplings. Furthermore, as Arthur just discussed in his talk, requiring the curvature to be small in the conical region generically forces the warp factor to be negative in a significant fraction of the compactification. And this is what he referred to as the singular bulk problem. Now, resolution of such singularity has been suggested, but any such resolution would necessarily modify the compactification geometry. So I would like to argue that a regularized local brane action is needed in order to capture the interactions between various bulk and brane fields, which are smeared in the four-dimensional effective field theory. Now, I should stress that our results are general for flux compactifications with branes, but for the sake of presentation, we sometimes use KKLT as a proxy. So to illustrate that a proper regularization is necessary for extracting physically meaningful results, so we could examine how the brane gauginos contributes to the 10-dimensional equation of motions. So casting this brane gaugino effects in 10 dimensions also allows us to treat all the ingredients of de Sitter constructions, such as KKLT, on the same footing. So whether they are branes, gaugino, oriental fold planes, or fluxes, they are just different sources of the stress tensor. So we could start with the 10-dimensional Einstein equations and trace over the 4-dimensional indices. This gives us a relation between the 4-dimensional curvature and a certain combination of the stress tensor components, denoted by minus delta here. So this kind of reasoning has been central in many no-go theorems because many sources we know have positive delta, and we need negative delta in order to get de Sitter. Well, there are sources with negative delta, but let's look at what happened with the gauginos and the anti-branes. In addition to fluxes, branes, oriental fold planes, gaugino condensate, and anti-D3 branes also contributes to this combination of the stress tensor that I denote by delta in the previous slide. You can infer the contributions from the respective world volume actions. Naively, these contributions are both positive, leading to some confusion in the literature. Now, 4-dimensional effective field theorists may dismiss this problem because this conclusion was drawn by substituting the gaugino bilinear by its expectation value in the UV Lagrangian, whereas gaugino condensation is an infrared effect. But by now, it's clear that this is not the devil. The misconception in this earlier work and subsequent works that follows stems from an unregularized brane action. The gaugino contributions is UV divergent. Without regularizing this brane gaugino action, we cannot extract any physically meaningful results. So a goal of our work, although not the only one, is to regularize the brane action such that physically meaningful finite quantities can be computed from 10 dimensions and compare with the 4-dimensional picture. And indeed, we have shown that the 10-dimensional action for the gauginos that we obtain reduces to the textbook supergravity formula in 4 dimensions upon compactification. So this is one of our targets. To see why this is a non-trivial task, consider the brane gauginal action, which was known up to quadratic order prior to our work. So you can see that there is a coupling between the gauginos and the background free-form flux. And knowing this coupling is already sufficient to determine the back reaction of the gaugino on the background flux for questions such as what is the force exerted by the gauginal condensate on a D3 brane moving in a flux compactification. This action is adequate. The problem is that this action is divergent on shell. Now, you may take Q from the codimension 1 case and try to complete the action to a perfect square. However, it does not work, at least not to our satisfaction. The perfect square structure still leaves us with a non-local tail. And to see why, notice that the localized source, J, has a coexact piece. And this coexact piece cannot be canceled by the free-form field strength, which is crossed by the Bianchi identity. This coexact piece, in fact, diverges when approaching the brane locus, even though the action is integrable. So this coexact piece is the source of non-localities. Similar non-localities also arises when one tried to obtain the 7 brane action by T-dualizing the 9 branes, and the quartic gauginal term so obtained depends on the brane transverse volumes. So this is another way to see why this non-locality would appear. Now, at the fundamental level, such non-localities are unacceptable. These actions are best approximations where the effects that should be localized to the D7 branes are smeared over the internal space. And for reasons given before, we need to up our game with a microscopic description if we want to accurately capture the interactions between various branes and bulk fields. Now, regularizing the D7 brane action while respecting locality turns out to be a very challenging task, and it has only been completed recently. So let me highlight some key observations we made. First of all, it proves useful to decompose the free-form flux into its imaginary self-dual and imaginary anti-self-dual components. Now we can try to bring this action into a perfect square form as suggested by supersymmetry, but now with these components. And you notice that there is no cross term involving the imaginary anti-self-dual flux with the gauginal because ISD forms and ISD forms are orthogonal. So this ISD part of the free-form flux by itself is not closed by the Bianchi identity and can have a coexact piece. And indeed, you can show, and we have done that in our paper, that the first term is finite. The next 2 terms follows from the fact that this Chern-Simon type coupling is topological. We can replace this field strength by the quantized harmonic piece. And this quantized harmonic pieces contributes to the D3 tuples, and hence they are finite. So we have successfully isolated all the divergences to this last term, which is manifestly local. Here I have shown a more general case where with multiple D7 branes, where I and J labels the branes. And the contributions for I not equals to J is finite and has a very simple interpretation. So the 7 branes wrap 4 cycles. 2 of them intersect on the 2 cycle. The volume of this 2 cycle is what determines this quartic coupling. And so this suggests a way to regularize the divergence for I equals to J. We could take 2 infinitesimally different representative of the same homology class. The volume of the intersection 2 cycles give us the finite piece after the regularization. This regularization procedure amounts to replacing the singular 2 forms, which causes the divergence, with smooth 2 forms in the same cohomology class. So with this insight, we can now write down a properly regularized local actions for the gauginal up to quartic order. But we have done more. We have gone further to express this action in a 10-dimensional covariant way in terms of the 8-dimensional gauginos living on the 7 branes. We then show that our 10-dimensional covariant action reduces to the standard 4-dimensional supergravity results for the gaugino upon compactification on the Calabi-Yau space. And furthermore, we check that the 4-dimensional curvature computed from our 10-dimensional action matches with the 4D analysis of KKLT. So let me walk you through some of these steps. Now, in order to implement the regularization consistently with 10-dimensional covariance and locality, we should aim to express our action in terms of the 8-dimensional gauginos. Lambda here, 4-dimensional gauginos, which have no place in the 8-dimensional action. Furthermore, the action written above still contains quantities like the Kähler form, the holomorphic 3 form, and the intersection volume. These are geometrical quantities defined with respect to the internal space. And we could trade these geometrical quantities with the internal covariantly constant spinors, chi. This internal covariant constant spinor is what pairs up with the 4-dimensional gauginos to an 8D fermions. Now, the bispinor representations of the holomorphic 3 form and the Kähler form are standard. To see how the last relation comes about, notice that the Poincare duo of the D7 brane divisor, which I denote by sigma here, is identified with the first Chern class of the line bundle, which defines sigma. And we can further identify the line bundle on the divisor with the normal bundle. So if you are a geometrical person, you are already satisfied at this point because we have managed to write down your action in a local way that does not depend on things that are not that are outside of the locus of the branes. But we would like to be able to write this in a covariant way in 10 dimensions. So I have to press. So we would like to press on for a little further. Using the fact that the internal spinor is covariantly constant, we could trade this curvature 2 form with the Riemannian curvature, and consequently, this covariant derivatives. So using the bispinor representation of the Kähler form and putting all these things together, we show that the intersection volume of the 2 cycles depends quartically on the internal spinor in the following way. The next step is to pair up this internal spinor with the 4D gauginos and express the action in a covariant way in terms of the 8-dimensional gauginos living on the 7 branes. After some very fierce manipulations, we finally arrive at this properly regularized local action for the 8-dimensional gauginos on the 7 branes up to the quartic order. Okay? So this is the action that Arthur also showed you earlier in his talk. And the point I like to reiterate here is only after a proper regularization can we extract physically meaningful results. In our case, this quartic gaugino couplings. So as a consistency check, we show that this covariant 10-dimensional action reduces to the standard 4-dimensional supergravity results for the gaugino upon Calabi-Yau compactification. For those who are familiar with flux compactification, this is a very straightforward step. All the heavy lifting was already done in deriving this 10D covariant action. So you could expand your Kähler form in the basis of oriented for even 1-1 form. And this in turn give us various intersection numbers on the Calabi-Yau. Now, different components of the 3-form flux can be written in terms of the 4-dimensional Gukov-Wavre-Witten superpotential and its covariant derivatives. Now, here we are only keeping track of the gauginos, Kähler moduli, and axial dilaton dependence, extending our analysis to include also the complex structure moduli is straightforward, but not more illuminating. You just have to turn on more components of the fluxes. So the end result is that the 10-dimensional covariant action that we showed you earlier reduces to the standard textbook supergravity results for the gauginos. Finally, we can compute the gaugino and the anti-brane contributions to the 4D curvature directly from 10 dimensions. Now, this is possible now because the gaugino action.
Gary, you have 5 minutes left.
Okay, I'm way ahead of my time, so I think I'm going to be able to finish it before. Okay. So now it is possible because our gaugino action is finite. The contributions to the 4D curvature, which we denote by delta earlier, is a measure of the scaling of the Lagrangian with respect to the overall volume modulus. So indeed, with only ISD flux and with no gaugino condensates and no anti-branes, the no-scale structure ensures that the 4D curvature vanishes. Okay. Now, the gaugino condensation breaks the no-scale structure, and you could use the 10-dimensional covariant action that we obtained and substitute the gaugino bilinear by its vacuum expectation value to compute this quantity delta. And you find that you reproduce what you may call the supersymmetric ADS minimum of KKLT in a subtle but very interesting way. So this is what this computation amounts to. At face value, the last term is subdominant in the large volume regime. When T is very large, this term parametrically is much smaller than the first term in bracket. However, this naively dominant term in bracket vanishes by the equation of motion. So we could make this more clear by writing the gaugino, by writing this expression in terms of the 4-dimensional gaugino potential as follows. The first term vanishes on shell, while we can get from the second term the on-shell value of the SUSY ADS minimum. Now, I should stress that the 10-dimensional covariant action I have given you earlier gives the gaugino potential only to leading order in 1/T in the large volume expansion. This is not a deficiency, but rather totally expected. Gaugino condensation is an infrared phenomenon, and you should not expect to get the full gaugino potential by substituting the vacuum expectation value of the gaugino bilinear in the UV Lagrangian. Rather, the subleading terms come from renormalization of the gauge coupling. So anti-branes makes very little difference to delta because of the wall factor suppression. The anti-branes lives at the end of the throat. But this does not mean that the anti-brane contribute nothing to the 4D potential. The same off-shell formula I have shown you earlier carries over to this case, even in the presence of the anti-branes, because delta the anti-D3, as I've just argued, is negligible. However, the on-shell value of the Kähler moduli no longer coincides with the minimum of the gaugino potential. It should be the minimum of the full potential instead. And so the anti-brane can uplift because of a small shift in the Kähler moduli along a very steep potential generated by the gauginos. So let me summarize. Like it or not, the Swarmland program has significantly elevated the level of discussions of de Sitter constructions in string theory. Much of the recent technical advances would not have been made, and this is progress. Our regularized brane gaugino action has alleviated one of the concerns of KKLT. Other concerns have been raised, for example, the singular bulk problem that Arthur talked about, the tadpole problem, and the challenge in getting small W naught in a global model that other speakers will talk about. But I would argue that a microscopic description of brane localized non-perturbative effects is a more fundamental issue that we need to address before we go further down these roads. I have given you several motivations for such a microscopic description. And as promised, we have completed the D7 brane action for the gaugino and the coupling to the three-form flux up to the quartic order. Now, the properly regularized action, as you have seen, is free of divergence and is local. We consider this as prerequisites for quantitative studies of de Sitter vacuum within the context of flux compactifications. As a consistency check, we show that our 10D covariant action reproduces the 4D supergravity results for the gaugino of point compactifications, and a direct 10-dimensional computation of the 4D curvature matches with the 4D analysis. It would be very interesting to confirm our findings with more direct computations. Impressive progress has been made in deriving the kappa symmetric D7 brane action, but not yet to the order which can compare with our results. But given the highly non-trivial consistency checks we have done, we don't expect surprises. So let me stop here. Thank you for listening.
Thank you very much, Gary. Have a nice talk. Thomas had a question first.
Yeah, thanks. Thank you, Gary. You stressed the importance of having a 10-dimensional covariant action. I would like to ask, do you think there's a 10-dimensional covariant equations of motion, which upon reduction give the equations of motion you are using?
So I should say that I'm only dealing with the 8 branes. Are you referring to the fact that type 2B is self-dual?
No, I'm referring to the fact that there was one specific step at which I believe you lose a 10-dimensional picture, and that is when you insert, which you should, the expectation value of the gaugino bilinear, and it depends on the volume. But the moment you do this, you lose a 10-dimensional picture. Why? If you would compute the 10-dimensional energy momentum tensor in the way we learn, you take the 10D action you wrote down, I take a variation with respect to the metric, then I have a 10-dimensional Einstein equation. If I then insert the gaugino of F, I will not get to the equations you wrote down. So I'm a bit confused with the logic of, we all find it important to have a 10-dimensional covariant action, but there are no 10-dimensional covariant equations of motion, and so, somehow by this.
Yeah, I think the step of replacing gaugino bilinear by its expectation value is a very subtle one, and we should be careful what we do and what to make out of it. And so that's why in the beginning I emphasize what we are after is not the gaugino condensate itself, but rather the proper description of the couplings of the gaugino with various different things. And so I defer the matching with KKRT to the very end because we don't consider that as the prime motivation. And several things that would make this substitution not complete. One of them was mentioned in my talk, that it would never get you the full gaugino potential. It will only get you up to all these renormalization effects, which would run the Lagrangian to the infrared. So we are not going for something, we are not trying to describe this gaugino condensation in the full 10-dimensional picture. There's some limitations. I hope that answers your questions.
I'm not sure, but I understand what you're saying. Yeah. Thank you.
Let's move to Ander for the last question.
Okay, well, thank you for the nice talk, Gary. So my question is about this term where you have the intersection between the different D7 branes. When you're considering the self-intersection between a brane with itself, are you considering like some configuration where the brane does some kind of weird cycle and crosses itself, or what do you have in mind when you're doing these computations?
Yeah, so you are imagining taking two infinitesimally different representative of the same homology class and have them intersect. And so, and And this also explains why you don't see this in Herjavec-Witten. In codimension 1 case, you don't have the rich structure to have this self-intersection. So by self-intersection, you are imagining that you start from a singular two form, you smooth it to some smooth two forms, and you do so by choosing different representative of the same class and compute the intersection. So it's a regularization procedure.
I see. Okay, well, I'm a bit confused about it, but maybe we can talk on.
Okay, absolutely.
It's a well-defined story. I mean, self-intersection of a cycle is just defined that way. It's in formal geometries, that's just a standard thing. That you really talk about self-intersection that way. That's exactly as Gary explained.
Yeah.
You have a divisor, you deform it. Whatever the two cycle is that is where they intersect is the self-intersection two cycle, and that's the same as the usual definition with the wedges.
Okay. Well, I don't have the intuitive picture, but okay, I need to just look it further.
A very quick
Okay, Luca, I give you 1 minute.
Yeah, just 1 minute. So related to Andre's question. So, but when you do this regularization, you have to pick a representative. So how much does your result depend on this choice of representative?
Well, if it is a topological quantity, it should not depend. Right? So
Your final action is not topological, no? Your final action, the D7 brane action, in principle, you have the fields are of shell, so you don't have any, you are not integrating just, how to say, closed forms.
So maybe I'm saying something very simple in a complicated way. All I meant is that the quartic coupling is given by this intersection. So whether they are the same brane or different branes, and the question is how do you compute it for the same brane? And there's a well-defined procedure, which, as Arthur re-emphasized, is how you compute the self-intersection of the 7 branes. I mean, this kind of self-intersection also appears in F theory. And I think we have seen such possibilities before. For simple, non-curved branes, you don't see this.
Oh, sorry, I thought that you were using this cycle also for the D7 brane method, the fermions on the D7 brane, not just for the bulk model. I find, I mean, I can see that if you put the bulk on shell, you are coupling them to close form. But when you couple, you write down this coupling to fermions on the D7 brane. You had a slide with the D7 brane, with some D7 brane couplings, no?
Right. So the fermions are here, and this you could compute without talking about the fermions.
Okay, the fermions are generically.
These are overall factors. These are quartic gauginos terms, and the couplings of these fermions are dictated by these intersection numbers.
Okay, we should stop the discussion here. I'm sorry.
We could continue that on Slack if it's not clear.
Please do so.
Thank you.
So thanks again, Gary, for the nice talk, and we will move on with Irene.